Okay, good morning, class. Today I'm going to give you a little bit basic information about fatigue and fluctuating stresses. Okay, let me write the title for this today's video. Okay, this topic deals with the forces which which depends on time and they change as time passes. So force should be something like this, a function of time. So if I draw a graph for force, for this case, this is time, the y-axis is going to be force. This graph is going to be like this. So it changed by time. Okay, so if force changes as time passes, we are going to have variable stresses. Now, and you should know, if we have a variable stresses, our design is going to fail much earlier than reaching ultimate stress or yield stress. And that is why we consider fatigue as a really important topic for civil and mechanical engineers, because most of the time we have fluctuating forces like a wind, cars passing over the bridge, or any like a buildings because of the earthquake. We have some force fluctuating or stress fluctuating. So you shouldn't design your geometry for the ultimate stress or yield stress failure. You need to consider fatigue parameter. So now let's see what is going to happen if we had a fluctuating stress. Let's see. This is black. So this is my time axis and this one is my stress. Sometimes we show as sigma or S. And my fluctuating force is going to be like this. Beautiful. Let's define a few parameters here. The maximum one, we call it maximum stress. This one, minimum stress. The mean one, mid-range stress. And this part, alternating stress. Okay. And the relations between these parameters are as follows. So for mid-range stress, which we showed sigma m, we can find by this formula the average of sigma max and mean. You can get mid-range stress. For alternating stress or sigma a, you can find subtracting sigma mean from sigma max divided by 2. And we have stress ratio. We show it as R, and it is sigma mean over sigma max. Okay, now we know what is alternating stress, what is mid-range stress, and we are going to use them a lot more. Okay, let's see how stress is going to change. I'm going to plot a famous graph. We call it SN diagram. This SN diagram we usually draw for reversible loadings. So it is going to be something like this. First, I'm drawing without details, and then later I am going to add more details to it. So this one must be alternating stress, and this is going to be N, and N is cycles to failure. Let me write. Cycles to failure. And usually this is logarithmic scale, 10 power 3, 10 power 4, and more. Okay, so we expect to have this type. Now I'm drawing actual. By the way, let me explain something before going further. We talked about why we shouldn't design our geometry for ultimate stress or yield stress. We need to design for something lower, because there's a reason for that. Because before reaching those stresses, we usually see crack propagation when we have cycling loading. So if I draw, this is for example our cross section, and we have this stress profile here. This is static load. Static load. Probably it is going to fail when we have yield stress, or when we reach yield stress or ultimate stress. But for cycling load, we are going to have different behavior. Uniform here, over this crack, very high. Uniform, very high. Then again uniform, another crack, very high stress. So as you can see, one of those cracks, close to that crack, we could reach that ultimate or yield stress, and our system is going to fail. So that is why it is important we consider the number of cycles to reach that failure and prevent that crack propagation. So let's draw our SN diagram with full details. This is the number of cycles to failure, and this one is stress. And you know which stress I'm talking. It's alternating stress. We already talked here. Okay, usually we have these ones. Okay, first piece. Sharp decrease here. Second piece. And flat here. Okay. This point is ultimate stress. The other point, we call it SM or sigma M. And sometimes people define as 0.9 of ultimate stress or 0.75 of ultimate stress. Depends. This point we call it SE prime. And it is ideal endurance limit. Okay, let's show the value for the number of cycles. These are the approximate numbers. Usually this is 10 power 3, this one is 10 power 6. For this area, we call this one low cycle fatigue, which is less than 1000 cycle. Usually we don't design for this area. That is why if you check some textbooks, sometimes they don't include this area, and their SN diagram starts from 1000 cycle. Okay, the second area is going to be this one. We call this one high cycle fatigue area. We may design for specific cases for this area between 1000 to 1 million cycle. And finally, we have this area. Which we call it infinite lives area. So if you design your object for life cycle of more than 1 million, we call it infinite life. Usually we design for this life cycles. So our target most of the time is reaching 10 power 6 cycle, which we call it infinite life. If it's less than that, usually you should expect some failure, and we don't design for less than 1 million cycle. Okay, let's see what else I can add to this. So let's not to forget about this one. Usually it's a log scale. As you can see here, 10 power 3, 10 power 5, 6. We change like that. Okay, let me talk a little about this SE prime. So SE prime is ideal endurance limit. SE prime. This is the ideal case, and Because you want to have infinite life, you design your geometry for the endurance limit, which is usually much smaller than ultimate stress. That is why when you design something with cycling loading, you need to consider much lower stress for your design stress. Usually, for example, for steel, SE prime, we consider half of ultimate stress. Or for aluminium, SE prime, sometimes we consider 0.4 SUT, so 40% of ultimate stress. So you can see how big differences between static load and cycling load. And that is why some people, when they design for static load and their design has some cycling loading, later they are going to have very like disastrous failure for lower stresses because their design reached SE prime or ideal endurance limit. Why I'm repeating ideal endurance limit? Let me write it, the name here. Ideal endurance limit. Why I'm just repeating this ideal? Because we have endurance limit, which is this formula. So this ideal endurance limit, which usually is 50% of the ultimate stress, is also can be much lower. How? Because based on this formula, if you want to find endurance limit, which is this, you are going to multiply that ideal endurance limit with some correcting coefficients or factors. For example, the first one is load factor. If it's bending load, this coefficient is 1. For other loads, maybe it could be half or 0.7. Second one, it's a size factor. For some sizes, you need to consider smaller endurance limit. So we have some formulas for size factor too. The next one is surface factor. If your surface is very rough, full of cracks, yeah, you are going to have even smaller endurance limit. So we have some tables. If your surface is, I don't know, they prepared that surface, the cracks are much like a minimum, you may have like a close to 1 cc. If it's the quality of surface is lower, you may have like a 0.7, 0.4, 0.2, which is going to affect your endurance limit. Or this one could be temperature. And higher temperature, you are going to have lower endurance limit. So based on the temperature, depends on the material, you are going to have these correcting factors. And those factors are going to result in your endurance limit. Okay, let's go one step further. So now up to this stage, we understand when we have a cycling loading, the stress, the failure stress would be much smaller than ultimate or yield stress. Okay, let's consider static loading, static mode. So When I say it's a static mode, it means stress and time graph is going to be like this, constant as time passes. Therefore, if I draw sigma A and sigma M, which was alternating stress and mid-range stress graph, it is going to be over x-axis, which is mid-range stress. And that point is going to be here. Oh, we call it ultimate stress. It is going to fail over ultimate stress, and we don't have any alternating stress because it is static mode. Let's consider fully reversible loading. This is my fully reversible loading graph. This is sigma. It is fully reversible, positive, negative, positive, negative. And for example, this can be 20 megapascal, so the lower part must be negative 20, because the name shows that it is going to be fully reversible. And I claim that sigma M, or mid-range stress, is 0. You can see here mid-range is here, sigma M. Or based on the formula, we can see that sigma M is 20 plus negative 20 divided by 2, which is going to be 0. So if I draw sigma A, sigma alternative stress and mid-range stress graph, it is going to be here, and it is going to fail at endurance stress. Am I right? Because sigma M is 0, so the failure point must be over y-axis, which is alternating stress, and alternating stress is, because of this being cycling load, it is going to be SE, or endurance limit. So we had two cases. Somebody really clever named Goodman said, let's combine those two and create a criteria. Let's see what Goodman said. I'm going to tell you Goodman line. So this is sigma A and sigma M. Goodman said, we know that for static one, we have this ultimate stress important. For cycling one, endurance limit is important. Let's connect those two. And that line is going to be decision-making line. If your design condition was under this one, you are going to have infinite life. If it was above this line, you are going to have finite life. So it's a tool for engineer to decide if their design is going to be part of like infinite life or finite life. Okay, let me add one more line. We have another decision-making line, which we call it Langer line or yield line. And those 2 points, the points for that line are yield stress. So this is our yield stress and yield stress here. And the line connecting those two sorry, I'm doing my best to draw a straight line. Is going to be our yield or Langer line. Okay, we have many other lines for making decision if our design is going to have infinite life or finite life. The most famous one is Goodman's line. And the formula for Goodman's line is this: sigma A divided by SE plus sigma M divided by SUT is equal 1 over N. If this N was bigger than 1, you are going to have infinite life. If N was less than 1, they're going to have finite life. Yeah. So ANSYS can do this calculation for us. As you can see, you need to have all the stresses like ultimate stress, alternating stress, mid-range stress, SE, to be able to calculate this N number and show us what is the cycles, how many cycles we can have before reaching failure. And as you can see, because we need those numbers to be able to solve fatigue, so fatigue calculation is post-processing calculation, not part of initial calculation. So ANSYS is going to solve all the stress strains and then using those data to calculate fatigue. And the good thing about ANSYS can do this fatigue calculation for all those mesh points because they have different maximum minimum stresses those areas, and you can find the local area of your design with lower cycle of life, which you need to redesign or increase or decrease the load to make it above 10 power 6 or 1 million life to be able to claim you have a design with infinite life. Okay, I think I gave you good enough starting point. If you were interested, later read the textbook, documents, and you can always come back to me and ask questions. Okay, see you next time.